In this lesson, we're thinking about molecular structure and acid-base strength. Basically, we're going to look at molecules and we're going to think about the electronegativity of the atoms and the number of oxygens to tell us how strong of an acid or base we have. Let's start by just comparing an acid and a base. We'll take a common base, and for this base, we will take sodium hydroxide, which is NaOH. And we'll compare that to an acid, and for our acid, we'll take HClO. Now, you might remember that when you see this OH, that's a good hint that we have a base. And when it starts with an H, that's a good hint that we have an acid. And so one's a base and one's an acid. But if we look at their molecular structure, they're quite similar. So this base has a sodium attached to an oxygen attached to a hydrogen, while the acid has a hydrogen attached to a chlorine attached to an oxygen. So we'll start, just so we can make a good comparison, with the chlorine going to an oxygen, going to a hydrogen. Now there's some lone pairs here, but we're not going to worry about that for now. All we're really going to do is think about the bond strength. The only difference between these two molecules is that one has a sodium and one has a chlorine. Now, chlorine turns out to be pretty electronegative, which means it loves electrons. What that means is it draws this bond towards it. Why? Because the bond is made out of electrons. Remember, that's what bonds are. And so because chlorine is electronegative, it draws that bond towards it. And what that means is that this whole thing kind of functions as a unit. It stays together because chlorine really wants those electrons on the bond. On the other hand, sodium is not very electronegative. In fact, oxygen is more electronegative than sodium. And so the opposite thing happens here, where the electrons in the bond shift towards oxygen. And what that means is that this oxygen and hydrogen functions as one unit. Okay, why does this matter? Well, when they fall into water and they split apart, this bond is going to break here because the OH is so tightly glued together, and that's going to release an OH minus, or a hydroxide, which is a proton acceptor and a base. On the other hand, if our acid is put into water, it's going to split here, and this hydrogen is going to come off. And that means that it'll act like an acid, because a proton being released into solution is what an acid is. Okay? So we have here molecular structures that are really similar. And what explains why one of them is a base and one of them is an acid is electronegativity. And that's the first thing we're going to look at to think about acid-base strength. All right, so in this case, we just have a generic EOH written, and that E could be anything. So it could have been, in our previous case, our sodium or our chlorine, and it's connected to an oxygen and a hydrogen. These three lines don't have anything shown off of it because they could be connected to something or not. All we're worried about is this E. And here's the rule. If the electronegativity of E is greater, that makes it more acidic. So the more electronegative E is, the more acidic the compound is. And that allows us to compare the strengths of different acids and bases. So, for example, let's take this list of acids. It says, which of the following is the most acidic? HCl, HBRO, or HIO? Well, the only difference, just like we've been looking at, is that atom that's not oxygen or hydrogen. So chlorine, bromine, iodine. And if we want to know the strongest one, then what we need to do is compare their electronegativities, which we can do here on this electronegativity table. So chlorine has an electronegativity of 3, bromine has an electronegativity of 2.8, and iodine has an electronegativity of 2.5. Remember, the bigger that number, the more electronegative, the more they want those electrons, and that means the more easily the hydrogen will come off, making it act like an acid. So the one that's most electronegative gives us the strongest acid. Which one's most electronegative? You guessed it, chlorine. And so that makes the strongest of these acids HClO. So the strongest of our acids here would be HClO. For fun, I know you're going to think it's a blast, right? For fun, let's do the weakest. Which one would be the weakest? Well, exactly the opposite, the one with the lowest electronegativity, which we see here is iodine. And so the very weakest of our acids would be HIO on this list. So that's how we can use the electronegativity there of one of our atoms to tell us how strong of an acid is. The more electronegative, the stronger the acid. Okay, great. Now let's think about the impact of oxygen. Once again here, this really has to do with electronegativity. So I've put our electronegativity table up on the right, and then we're comparing nitrous acid, which has 1, 2 oxygens, and we're comparing that to nitric acid, which has 1, 2, 3. We're going to really focus on the oxygens not connected to the hydrogen, okay? So let's focus in on those. When we think about our electronegativity, we compare oxygen to nitrogen, and we'll see that oxygen is more electronegative than nitrogen. So what that means is our electrons here are drawn towards oxygen, and that's happening over here as well. But because in the case of nitric acid, we have two oxygens drawing those electrons, that makes that nitrogen hold ever more desperately onto this oxygen, okay? And it weakens the bond right here. So what that means is the more oxygens you put on that non-oxygen atom, the stronger the acid. So here's how we can summarize that rule. The more oxygen, the more acidic. Pretty straightforward, ultimately, when you summarize it that way, right? More oxygen on our nitrogen means it's more acidic. So which one of these is going to be more acidic? Well, the one with more oxygen, which is nitric acid. So this one's stronger. And in fact, it's a strong acid. It completely dissociates in water, whereas nitric acid turns out to be a weak acid. And it all has to do with that extra oxygen. Okay, so we've learned two rules. One is the more electronegative our non-oxygen or hydrogen atom is, the more acidic. And the other is the more oxygen, the more acidic. Let's apply now this second rule. Rank the following acids from strongest to weakest. Well, remember that more oxygen just makes something a stronger acid. And so the very strongest, if we start with the strongest first, is going to be the one that has the most oxygens, which is HClO4. And we'll get weaker when we remove one of those oxygens to HClO3. We'll get weaker still when we remove another oxygen to HClO2. And we'll get weaker still when we go to HClO. So this over here would be our weakest. So that is how we can rank them from weakest to strongest based on the number of oxygens. The more oxygens, the stronger. That's the basic rule. Okay, so we've been talking a lot about acids. Let's think about what this does to what we call our conjugate bases. So remember, we introduced conjugate bases in a previous lesson. And just as a way of a reminder, let's draw the conjugate bases for each of these, okay? So all we got to do to generate their conjugate bases is get rid of their hydrogen. All right, so HClO, I'm going to remove the hydrogen. That's the sound a hydrogen makes when it comes off, little known fact. And it becomes ClO minus. It's minus because the hydrogen was positive. Next, we just get ClO2 minus. We again just remove the hydrogen. And you can see the pattern here, ClO3 minus and ClO4 minus. Okay, now we're in a position where we can think about the strength of these conjugate bases using the same exact rule we had before. So let's do that. All right, so remember, this was the strongest acid, right? What does that mean? That means it gives off hydrogen the easiest. So this guy hates hydrogen. Okay, that's a little anthropomorphic, but whatever. It hates hydrogen. It doesn't care if it's on there or not. It would rather the hydrogen just float away. So that means when we come down here and we think about ClO4, it doesn't really care if it grabs a hydrogen that's floating around in solution. And so that means it's not going to be a very good base. Let's compare that, though, to this guy. This guy doesn't have many oxygens, and so it's a pretty weak acid, and it loves its hydrogen. That means that it really wants to stay with it. So when this guy comes along and sees a hydrogen in solution, it's going to be pretty good at grabbing it. All right, so what that means is the strength of our conjugate bases is exactly the opposite trend of our acids. They increase as they go this way because the less something wants a hydrogen, the less good of a base it is, right? And so if it doesn't really want to grab that hydrogen in solution, it doesn't want to act as a proton acceptor, then it's going to be a weaker conjugate base, okay? So the strongest conjugate base here is ClO minus. And the weakest conjugate base is ClO4 minus. So now we can summarize our rules for acid and our rules for conjugate bases. Remember that for acids, more oxygen makes it more acidic. And it's exactly the opposite for conjugate bases. More oxygen makes it less basic. Then we have our electronegativity rule, which tells us that the more electronegative that non-oxygen or hydrogen atom is, the more acidic. And again, exactly flipped for conjugate bases. The more electronegative that atom is, the less basic. Okay, so now we can apply our conjugate base rules to these two problems. The first one, rank the relative strength of the following conjugate bases. So it tells us it's conjugate bases. We can see that because they're negatively charged. We could make acids out of them by adding the H. And what we're really asking here is which one of these wants H the most and which least, right? The more it wants an H, the more basic it is, because remember, a base is a hydrogen acceptor. Now, our rules for conjugate bases, which you should just write down and commit to memory because it's easy to flip-flop this stuff, so just memorize it, is that the more oxygen we have, the less basic, okay? So if we go from strongest to weakest, strongest is going to be the one with the least oxygens, so NO minus. Remember, this is strongest in terms of being a base, not an acid. And now we have NO2 minus because it has one more oxygen, gets a little weaker. And then NO3 minus gets to be the weakest. All right, so that's ranking them from strongest to weakest, where we're using the rules about oxygens. Now we're going to use the rule about electronegativity. It says rank the relative strength of the following conjugate bases, and we're given ClO2- and O2- and SO2-. Now notice the oxygens are staying the same, and the only difference is that non-oxygen atom, okay? And the rule here is the more electronegative, the less basic. So let's compare the electronegativities of chlorine, nitrogen, and sulfur. So here's chlorine, here's the sulfur, and here's nitrogen. What we see actually is that the nitrogen and chlorine tie with the most electronegative. Meanwhile, sulfur is the least electronegative, okay? So sulfur having the lowest electronegativity would be the best base. And so SO2 is going to be the strongest. So again, when we think about listing the strongest, we're going to start with SO2-. The next two are a tie. So I'll just stack them on top of each other. We have NO2- and ClO2-, which, as far as we know, tie. Okay? So that's how we can tell the relative strength of acids and their conjugate bases with these two rules about oxygen and electronegativity.